Astronomers thought they had found evidence for a ninth planet lurking in the outer solar system. Then, a cosmic fossil called Ammonite showed up and threatened to unravel everything. Let's rewind to January 2016 when two Caltech astronomers, Konstantin Batygin and Mike Brown, dropped a bombshell on the astronomical community. They published a paper claiming they had found evidence for a ninth planet in our solar system, not Pluto, which had been demoted to dwarf planet status a decade earlier, but something much larger and much more distant. Their evidence wasn't a direct observation of the planet itself, but rather something far more subtle and intriguing: the strange behavior of objects in the outer reaches of our solar system. Specifically, they were looking at a group of trans-Neptunian objects, chunks of rock and ice that orbit the Sun beyond Neptune's path. Now here's where things get interesting. When Batygin and Brown analyzed the orbits of these distant objects, they noticed something that shouldn't happen by chance. The objects weren't scattered randomly around the Sun as you might expect. Instead, their orbits were clustered together, all pointing in roughly the same direction. It was like finding all the cars in a parking lot facing the same way. Possible, but highly unlikely, without some organizing force. The mathematical odds of this clustering happening by pure chance were astronomical. About 1 in 15,000. That's the kind of statistical significance that makes scientists sit up and take notice. But what could be causing this cosmic choreography? Batygin and Brown's answer was elegant and bold. A massive planet, roughly 5 to 10 times the mass of Earth, orbiting the Sun at an incredible distance. This hypothetical Planet 9 would be so far out that it would take between 10,000 and 20,000 years to complete a single orbit around the Sun. To put that in perspective, when this planet was last at its closest point to the Sun, humans were still living in caves and mammoths roamed the Earth. The proposed planet wouldn't just be distant, it would be on a highly elliptical orbit, swooping in as close as 200 astronomical units from the Sun and swinging out as far as 1,200 astronomical units. For comparison, Neptune, our current most distant planet, orbits at about 30 astronomical units. But Planet 9's influence would be profound. Its massive gravitational field would act like a cosmic shepherd, herding these distant trans-Neptunian objects into the aligned orbits that Batygin and Brown observed. The planet's gravity would also explain other puzzling features of the outer solar system. The hypothesis was compelling enough to launch a global search effort. Telescopes around the world began scanning the skies, looking for the telltale motion of this elusive ninth planet. The search area was enormous. Planet 9 could be anywhere in a region of sky covering thousands of square degrees. In the years following the initial announcement, the evidence for Planet 9 seemed to strengthen. Additional trans-Neptunian objects were discovered, and many of them fit the predicted pattern. The clustering became more pronounced, and computer simulations showed that a planet with the characteristics proposed by Batygin and Brown could indeed produce the observed orbital architecture. One particularly compelling piece of evidence came from objects called sednoids, a rare class of trans-Neptunian objects named after Sedna, the first of their kind to be discovered. These objects have some of the most extreme orbits in the solar system, with perihelia that keep them perpetually in the outer solar system. Sedna itself was discovered in 2003, and for over a decade it remained unique. Then in 2012, astronomers found 2012 VP 113, another sednoid with similar characteristics. By 2016, when the Planet 9 hypothesis was proposed, astronomers knew of 3 sednoids, all with orbits that aligned with the Planet 9 prediction. Computer simulations supported this scenario. When researchers modeled a solar system containing Planet 9, they could reproduce not just the clustering of trans-Neptunian objects, but also the specific orbital characteristics of the sednoids. The simulations even predicted how many sednoids should exist. For several years, it seemed like Planet 9 was the best explanation for the strange architecture of the outer solar system. The hypothesis made specific, testable predictions, and new discoveries continued to support it. Major observatories dedicated significant time to the search, but science has a way of humbling even the most confident theories, and the Planet 9 hypothesis was about to face its biggest challenge yet. In May 2023, astronomers using the Subaru telescope atop Mauna Kea made a discovery that would send shockwaves through the Planet 9 community. They found a new trans-Neptunian object, officially designated 2023 KQ-14, but nicknamed Ammonite by the research team. Ammonite was special for several reasons. First, it was the fourth known sednoid, joining the exclusive club of objects with perihelia beyond 50 astronomical units. The discovery of a fourth member of this rare population was exciting in itself, but as astronomers analyzed Ammonite's orbit in detail, they realized they had a problem. Unlike the three previously known sednoids, Ammonite's orbit didn't align with the others. Its apsidal line pointed in a completely different direction, breaking the pattern that had been one of the strongest pieces of evidence for Planet 9. This wasn't just a minor discrepancy. The Planet 9 hypothesis specifically predicted that sednoids should have aligned orbits. Ammonite's misaligned orbit was like finding a car in that parking lot facing the wrong way. It suggested that maybe the organizing force wasn't as powerful as previously thought, but Ammonite wasn't the only troublemaker. Around the same time, astronomers announced the discovery of another problematic object, 2017 of 201. Computer simulations of the Planet 9 scenario suggested that this object shouldn't exist at all. According to the models, if Planet 9 were real and located where the hypothesis predicted, its gravitational influence should have ejected 2017 of 201 from the solar system millions of years ago. Yet there it was, stubbornly orbiting the Sun in defiance of the theoretical predictions. These discoveries represented fundamental challenges to the Planet 9 hypothesis. The astronomical community began to take notice. Papers started appearing that questioned the statistical significance of the original clustering. As challenges to Planet 9 mounted, astronomers began exploring alternative explanations. One of the most intriguing alternatives came from stellar archaeology. What if the unusual orbits weren't caused by a hidden planet at all, but by an ancient encounter with another star? This stellar flyby hypothesis proposed that billions of years ago, during the early history of our solar system, another star passed close enough to gravitationally perturb the orbits of distant objects. Such close encounters aren't far-fetched. Our Sun formed in a stellar nursery surrounded by hundreds of other young stars. A stellar flyby could explain many puzzling features of the outer solar system in one fell swoop. The passing star's gravity would have stirred up the orbits of distant objects, creating the clustering and extreme orbits that we observe today. Recent research has made this scenario even more compelling. In 2024, a team of astronomers published a detailed study that traced the possible trajectory of such a stellar encounter. They showed that a star passing within about 100 astronomical units could produce orbital patterns remarkably similar to what we observe. The stellar flyby hypothesis has several advantages over Planet 9. First, it doesn't require an undiscovered planet. Second, it can naturally explain the diversity of orbits in the outer solar system, including misaligned objects like Ammonite that cause problems for Planet 9. Today, the Planet 9 hypothesis finds itself at a crossroads. What once seemed like a slam-dunk case for a hidden planet has become a complex scientific debate with passionate advocates on multiple sides. The original Planet 9 team, led by Battigan and Brown, hasn't given up. They continue to refine their models and search for additional evidence. They've argued that the clustering signal remains statistically significant and propose modifications to accommodate problematic objects. On the other side, the skeptics have grown more vocal. Multiple independent analyses have questioned the statistical significance of the original clustering, with some studies finding no evidence for alignment once observational biases are properly accounted for. But perhaps the most important development is the recognition that we need more data. The Vera Rubin Observatory, currently under construction in Chile, promises to revolutionize our understanding of the outer solar system. It's expected to discover tens of thousands of new trans-Neptunian objects. The Planet 9 debate represents more than just a disagreement about a single planet. It's a perfect example of how science works at its best, and how even the most compelling theories can be challenged by new evidence. The story also shows how modern astronomy operates as a global, collaborative enterprise. The discoveries that have challenged the hypothesis have come from telescopes around the world, operated by international teams of researchers. The next few years will be crucial for resolving the Planet 9 debate. Direct detection efforts continue, and the James Webb Space Telescope represents a new tool in this search with its incredible infrared sensitivity. Whatever the outcome, the Planet 9 saga has already advanced our understanding of the solar system. it has focused attention on the outer solar system, leading to dozens of new discoveries and driving the development of new theoretical models. The story of Planet 9 and the objects that challenged it is far from over. What started as a compelling case for a hidden planet has evolved into a complex scientific debate that touches on fundamental questions about how our solar system formed. Objects like Ammonite, that cosmic fossil with the misaligned orbit, represent more than just challenges to existing theories. They're reminders that the universe is under no obligation to conform to our expectations, and that the most interesting discoveries often come from observations that don't fit our models. Whether Planet 9 exists or not, the search for it has transformed our understanding of the outer solar system. We've discovered that this distant realm is far more complex and dynamic than we previously imagined, populated by objects with exotic orbits that challenge our theories. So the next time you look up at the night sky, remember that out there in the darkness, far beyond the reach of our eyes, a cosmic detective story is still unfolding. And somewhere in that vast expanse, the answer to one of astronomy's most intriguing mysteries is waiting to be found.